Welcome back to AP Physics Made Easy. If you're taking AP Physics or really any physics class and you need a little bit of help, you've come to the right place. My name is Eric Sampson. I've been teaching physics concepts for the past 40 years, and I'd love to help you with it. So in this episode today, we're going to be looking at motion graphs. Let's get started. So on the AP Physics test, you're going to be expected to extract a lot of information from these graphs. So let's look at what types we have. We have three types of position graphs. In all three of these graphs, the x-axis is going to be time, and usually that's going to be in seconds. You know what? That's always going to be in seconds, come to think of it. And then we have a position graph, a velocity graph, or an acceleration graph. So the y-axis changes, but the x-axis is always time. So let's start with position versus time graph. So on a position versus time graph, as we said before, the x-axis is going to be time in seconds. The y-axis is where the object is, its position, and it's usually going to be given to us in meters. Now, let's just say I have a person, an observer, standing here, and what's going to happen is I look here at time t equals 0. What this negative 20 is telling me is this object is located 20 meters to the left of the person. So 20 tells me how far, and negative tells me it's to the left of the person. At t equals 2 seconds, I can see here that the value I get for the position is negative 10, and that means it's located 10 meters to the left, the negative direction of the observer. Then at t equals 0, t equals 4, I see it's 0 meters away. Maybe it ran him over, or maybe it's right in front of him. We'll assume the best for this poor person. Then at time equals t 6 seconds, I see it is now positive 10. That means it's 10 meters away from him in the positive direction, and then 20, and then 30. The slope is something we need to focus on. So the slope of the line, there's three things you want to ask yourself anytime you look at a motion graph. You want to say, what do the y values mean? What does the slope mean? And what does the area under the line mean? So let's look at what the slope is for this position versus time graph. It's going to be the velocity. And a good trick for doing that is to remember that slope is always change in y over change in x. So what you do is you substitute in these values here from your graph. My y values, the units are meters, and my x value is in seconds. So meters over seconds, hey, that's velocity. This is a really good trick to use. Just look at this here, whatever this unit is here, divide it by seconds, and actually, what is that a measure of? Meters per second is velocity. Meters per second is acceleration. Trust me, this is a great trick to use. Okay, so in this case here, mathematically, I want to be able to determine what is the velocity. This is something you'll do a lot in AP Physics. Unfortunately, it's not that difficult to get the slope of this line. So velocity is equal to change in position over change in time. So in this case here, the change in position was, my final position was positive 30 minus my initial position, which was negative 20. So you got to be careful when you're working with vectors to remember those positive and negative symbols. And so when I solve for this, what I'll get is a velocity of positive 5 meters per second, which that means basically is that with each passing second, the object can travel 5 meters in the positive direction. So after 1 second, it goes from negative 20 to 15. That's 5 meters in the positive direction. It goes from negative 15 to negative 10, negative 10 to negative 5, and so on. So that's one way of interpreting what this means. So on a position versus time graph, the slope is telling me the magnitude of the velocity vector, and its direction can be determined from the angle it makes. So here I see I have a gentle upwards one. So the fact that it's upward tells me that it's a positive velocity. It's moving in the positive direction, but the slope is gentle, meaning it's not going very fast. Here I see I have a negative slope, meaning it's moving in the negative direction, and it's a steeper slope, so I know it's going faster. So I've got to be careful not to confuse the direction of the velocity with the positional direction. All right, so I've intentionally given you two graphs here, two lines on the same graph that have the opposite values for the velocity versus position. So let's just look at this first one here. In the first one, the object is traveling in the negative direction. I can tell because I have a negative slope. However, at all times between time 0 and time 10, it was always located in a positive positional value. Whereas if I look at the second one here, it's always in the negative range. It's never been to the right of me. It's always been to the left of me, but it's moving to the right. It's moving in the positive direction. I can tell because it has a positive slope here. And I can look at them and say, well, these slopes look to be the same. And if you calculate them, in both cases, the magnitude is going to be 2, but this is going to be negative 2, whereas this is positive 2. But just be careful. Just because the velocity is negative doesn't mean the position is negative. Now, a slope of 0 would mean the object is not moving. So let's just look at what I have here. Initially, this object at between times 0 and 6, I can tell I have a positive slope, so it's moving in the positive direction. If I calculate, I'll see it's 5 meters per second in the positive direction. But now I get to, at t equals 6 to t equals 10, it doesn't change. And remember, the slope is your velocity. So if the slope is 0, that means you're not moving, and that makes sense because its position stayed at 15 meters away from me in the positive direction for those 4 seconds. So for 4 seconds, it was the same distance away from me, meaning it's got a velocity of 0. Now, if the slope of the line is constant, that communicates something very important in AP Physics. It communicates that this object here has a constant velocity. Its velocity is unchanging, the object is not accelerating, and we will learn as we go through our course that means that the overall force acting on it is 0. But if I look at this one over here, I see that at this point here, this is a good trick to use. Look at the very beginning, near t equals 0, that slope is pretty close to 0, so this object was barely moving at all. And here the slope is quite steeper, so I know this object is accelerating. So a curved line tells me it's accelerating, and a straight line tells me that it is traveling at a constant speed. Now here's a really simple way to tell from a position graph whether or not the acceleration is positive or negative. I look here, I know that this is accelerating because it's curved, and I know this is accelerating because it's curved. But is it a positive acceleration or a negative? This is a great way of remembering, and it's just such a cheat, and it's this. Smiles are positive, so I look here, I see a smile. Smiles are positive. This is a positive acceleration the whole time. Regardless of whether the slope is positive or is negative or the slope is positive, whether it's located in the positive x value or the negative x value, it doesn't matter. If you see a smile, smiles are positive, the acceleration is positive. I look here, I see a frown. All right, frowns are negative then, right? So if smiles are positive, frowns are negative, and I know that this entire time, whether it's got a positive slope or a negative slope, whether in this case the whole time it's located in the positive positional range, it's still always a negative acceleration because it looks like a frown to me. So let's just try looking at it if you don't have a full smile or full frown. So often you'll see things like this. Let's just call these partial smiles and partial frowns. How about it? So let's look at this first one here. So I have this position versus time graph. I notice at first it's got a very small slope, almost 0, and over time it's becoming increasingly negative. I see part of a frown. Well, that's because it's a negative acceleration. Let's look at this one here. Again, I start off with a slope that's pretty close to 0, but over time it becomes increasingly positive. Even though I'm starting off in a negative positional range, it's still curving upwards. It looks like a smile, so that tells me that what I've got here is a positive acceleration. Let's keep going. Now here I start off with a pretty significantly positive velocity value because the slope is very positive, and the slope ends up being 0. So it's slowing down in the positive direction. Looks like a frown, and you know what? Slowing down in the positive direction, that's a negative acceleration. And then we're coming over here. I see a smile, guys, so that I know it's going to be a positive acceleration. Let's think about this. It starts off with a pretty steep negative slope, so it's moving quickly in the negative direction, and as time goes by, its magnitude becomes less and less until it reaches 0. Slowing down in the negative direction, well, that's a positive acceleration. If I have a velocity versus time graph, this is the one that tends to get kids into trouble, I'd say, and it's one that you get presented with the most. So velocity versus time graphs are really common in AP Physics because they communicate acceleration, and we're really interested in accelerations because they relate to forces. So again, we always want to look and see, what do the y values tell me? Well, the y values are meters per second, how fast the object is going. So the numbers are the magnitude of the velocity, and the positives and negatives tell me the direction of the velocity, which way you are going. Not where you are, but which way you are going. So if they're negative, it means you're moving in the negative direction, and if the values are positive, you are moving in the positive direction. So let's just walk through this graph and see what it can tell us. So at t equals 0, I see a value of negative 20. The object was moving 20 meters per second in the negative direction. And now it's moving at negative 10. Now it's moving at negative 5. And look what happens here. At t equals 4 seconds, the object has stopped just for an infinitely small amount of time. But it has stopped. And that's because it's changing direction. If you think about this, if you're moving to the left and you're going to start moving to the right, you have to stop moving so you have a velocity of 0. So think of this always as being a change in direction. So a velocity of 0 means you're changing direction. And now I'm beginning to move in the positive direction as I go this way. So my velocity becomes positive. Well, what does the slope of the line mean? Just like we did before with position, we're going to do this with velocity. So I'm going to look at this unit here and say, well, meters per second is y. So my change in y is going to be meters per second. And this is, you can't see it, but that's time. So I'm going to divide meters per second by seconds, and that gives me meters per second per second. Meters per second per second, that's acceleration. So the slope of the line in this case here is the acceleration of the object. So here I see a negative slope, so I know I have a negative acceleration. And if I calculate it, I'm going to say 0 minus 30 over 10, and that gives me an acceleration of negative 3 meters per second squared. That means each second is going negative 3, but it's going 3 meters less in the positive direction. Right? So let's look at the blue one here. So this blue one, I see a positive slope, and it looks to me like it's not as steep. So I think what's going to happen is I'm definitely going to get a positive acceleration value with a smaller value for my my magnitude. Sorry, I had a little brain fart there. All right. So again, so if I calculate, I'm going to see it's positive too. So I know it's positive by looking at the slope of the line, and I can tell by the fact that this is less steep than this that it's going to be accelerating at a slower rate. Now, the area under the line of a displacement, of a velocity graph rather, tells you what the displacement is. So think about this. And this is really important because they love to ask about area. So meters per second is my velocity value. My time is in seconds. And again, I'm sorry that got cut off here. So if I want to find area, I'm going to say y times x. If I want to find what this area is, I'd have to multiply the y value by the x value, right? Length times width. So when I do that, think about it. I'm going to substitute y with meters per second here. I'm going to substitute x with seconds, and when I multiply, the seconds cancel out, and I'm just left with meters. So it's going to tell me the displacement. So on a velocity versus time graph, if I take the area of this graph, and by the way, the area, I only go between 0 and the line. I don't go all the way to the bottom of the graph. This area is going to tell me what the displacement of the object is. So in this case, I would say 20 meters per second times 10 seconds, and the seconds cancel out, and that gives me 200 meters. That's the displacement of the object. And again, you only go from the line to 0. Don't keep going to the bottom or the top of your graph. Well, what do we do if the line is sloped then? Okay, here, if you're taking calculus, you know how you can take an integral, but this is an algebra-based class. We don't have to do that. So here's what's going to happen, and this is a really cool cheat. You just imagine a rectangle around that sloped area, right? So I take this rectangle, I'm going to find the area of this rectangle, and then divide it by 2 because this bisects it. So I'd say 30 times 10, that's 300. And then I divide it by 2 because the area under this line is only half of this rectangle, and I get 150 meters. This is a technique you'll use a lot this year. Now let's talk about acceleration versus time graph. Sorry, this one's going so long. So an acceleration versus time graph, the y values are the rate of acceleration. So this is the magnitude of your acceleration. We're accelerating at 20 here, 10 meters per second squared here, and this is telling me the direction. The acceleration is in the negative direction. The accelerations are in the positive direction. And the slope is worth pointing out in almost all cases in AP physics, with the exception of harmonic motion, springs and pendulums, we're always going to look at, and they say this in their course exam description, we're going to give you constant acceleration. So it's going to be a flat line. So you don't really need to talk about what the slope of an acceleration line is, but we definitely need to talk about what the area is. So the area under the line, well, let's think about this. Okay, remember this technique. We're going to say, well, area is going to be length times width, or y times x. So I'm going to look at what my y variable is. It's meters per second per second. So I'm going to put that here, meters per second squared, and then I'm going to multiply it by seconds, and these seconds cancel out, so I get meters per second. So what that tells me then is that the area here is the change in velocity, because remember, acceleration times time equals change in velocity. So this isn't telling me how fast you're going, it's how much you've changed your velocity. It's your delta v, not your v. Be careful with that. Okay, so let's just say if I calculate it here, what I'm going to get is 20 times 6, that's 120 meters per second of change in velocity in the positive direction. So whatever it was before, is going to change by 120 in the positive direction. For this area here, I'm going to have, let's see, negative 10 times 4. Remember, I got to remember that it's change in the change in x. So this is just 4 seconds, and so that's negative 40 meters per second. So the total change here that would have occurred if this accelerations had been applied to an object with an initial velocity of 0, then what I'd end up with is I'd added 120 meters per second, then I took 40 away, and that means I would have 80 meters per second of change. So let's take this graph and apply it to a problem. So let's just say we're told that at time t equals 0, we have a jet and it's traveling at 100 meters per second in the positive direction. And it is subject to these accelerations. So I'd first look here and say, okay, 20 times 6, that would be 120 positive delta v's. And here I have negative 10 times 4, so that's negative 40. So I just have to sum this up. So I'd say, well, the jet was initially going 100 meters per second. I added 120 in this section here. That was its delta V here. And then I had negative 40 meters per second in this section here. And when I add that all up, being mindful of my negatives, I get 180 meters per second. Thanks for watching. If you like this video, remember to like this video. Also, if there's something you think I could do to improve my videos, or maybe there's a different subject you'd like me to make a video on, please drop me a line in the comments section. One of the most important things to keep in mind about getting good at AP Physics is it's never going to happen unless you practice. So to help you out, I've put some practice problems in the description below, along with solutions documents. And I've made lots of other videos about AP Physics. I make them on pretty much every topic, so you may want to take a look at some of my other ones if there's a different area of the subject that you're having trouble with. And of course, more than anything else, it would really help me out if you would subscribe to my channel.